Hi, everyone. Sorry for the delay. I know I'm in between you and the lightning talks and the end of day one, but I promise I'll try to be quick. So I'll be talking about Python's Array API standard today and how we used it for a library, a Python library called Glass, which is then used at ESA's Euclid mission that was launched in July 2023. So I'll start by talking about Python and arrays, or more specifically, arrays in Python. So I'll introduce you to the Python Array API standard, then I'll introduce you to Glass and why we need the Array API standard, and then the work that we've done at UCL. Cool. So there once was Python with no arrays. I'm glad I did not exist when there was a Python with no arrays, and I'm sure no one liked that. You could not do much with Python. And some heroes decided to change that. So they came up with this library called numeric, or numerical Python. And it's so old that they used to distribute their binaries on sourceforge.io and not by PI. They created it in 1995, before I was born. And then some people were not even happy with numeric, and they came up with numarray, which was for niche array operations, or array operations on small arrays. And this was back in 2003. But finally, some people got together and decided to build a standard array library for Python, which we all know today as NumPy. You'd see that the logo is similar to numeric, and this was the oldest logo I could find in their Git history. And this was in 2006 when I was in kindergarten, good old days, when I didn't know what Python was, when I didn't know what software engineering was. And then they just kept building and building. And we have a lot of array libraries now in the Pythonic ecosystem, which is both good and bad for us. So all of these libraries provide users with some array functionality. So we'll call them array provider libraries, or provider libraries throughout this talk and even in the documentation of the Array API standard. And these libraries obviously were not required to have a certain API style. So you could create an array library and you could keep whatever API you want for it. A few of them intentionally kept it similar to NumPy because NumPy became a de facto standard a while back, and they only deviated when it was absolutely necessary. A few of them did not, understandably, and a few of them tried to, but it wasn't just a priority. And I know that QPy, for instance, is still trying to match NumPy's API, but the API is so extensive that you need a lot of work for it. But some libraries want to use these array libraries, or these provider libraries, for things like scientific computing or machine learning. And two big examples are SciPy and scikit-learn. So SciPy and scikit-learn do not have an array type of their own. They just take an array, perform some mathematical computation on it, and return you an array or a scalar, and so on. Or some libraries need arrays for large-scale cosmological simulations, very specific, but that's what Glass does. And we call these array consumer libraries, or just consumer libraries. And given how rapidly the provider libraries have been multiplying in the Python ecosystem, we do not want a fragmented consumer ecosystem. So for instance, we do not want a SciPy for NumPy, a SciPy for JAX, a SciPy for QPy. Similarly, we do not want a scikit-learn that works only for NumPy, one that works for QPy, one that works for JAX. So wouldn't it be nice that we had the same consumer library, SciPy, and you pass in any array, a NumPy array, a JAX array, a Dask array, and it just works out of the box? That is what brings me to the Python Array API standard. So a group of people got together again. This time, they did not build an array library. Instead, they created a standardized API. So they standardized the API for these provider libraries, and under the organization or the umbrella called Data API. So how does the Array API work? Let's say I had a function that takes in presumably a NumPy array because it's doing NumPy operations on it, a bunch of reducers or mixture of reducers and ufuncs. And what if I want this thing to work naturally with JAX, QPy, Dask, or any provider library? With the Array API standard, all I have to do is this. So Array API provides you with a whole document of functions, methods, properties, and so on, things that your array library should have that would make it compliant with the API standard. And once it's compliant with the API standard, you can basically do something like this. So the array namespace is a special method of these array libraries, which just returns the namespace in which your array functions are implemented. So for instance, if you pass a NumPy array in this, XP would just be NumPy. If you pass JAX in this, XP would be jax.numpy, because jax.numpy is the namespace where all of your array functionality is implemented. So XP technically is just an alias for your array namespace. And if you know that your provider library matches the array API standard spec, you know that all the functions that are used here and that are declared in the array API would work with the library. It is that simple. So now I can pass in JAX, Dask, or anything that adheres to the array API library arrays, and it'll work. But is it that simple? We'll talk about that in the next few slides. But also remember that this function will most probably already work with all the array libraries. So if you pass a JAX array, there are chances that it'll work completely naturally, because these big popular provider libraries already support most NumPy operations, or they override these NumPy operations internally and dispatch their own functions instead of using NumPy functions. So something that happens under the dunder array ufunc method when you're subclassing NumPy arrays. But if a new library pops up biased array and it decides that, oh, we will not work with NumPy functions. So this thing will not work for the biased array library, but array API will still work. This thing will always work for the biased array library. And the key takeaway here is that array API does not talk about library interoperability. That is something, a cherry on top. So if you have JAX or NumPy, and NumPy works for JAX functions and JAX works with NumPy functions, that's something that they've added on top, but not specified in the array API. Array API standard only says that, oh, here is JAX, here is NumPy. Independently, both of them will have a subset of an API, which would be standardized. So again, no interoperability, only standardization. Cool. So now we know we have a background about the array API. Now I'll talk about what's Glass and why did we need array API for Glass. So Glass, or generator for large-scale structures, is a library for performing simulations that are often or very useful in the field of cosmology. These are simulations for modeling complex astrophysical properties, validating implementations, and performing inferences. So and this will be extensively used by missions like Euclid and the square kilometer array that's being built. So let's say Euclid as a satellite is taking a lot of data from the universe, and now we want to validate it against our existing theories. What we do is we create very realistic simulations of the universe, and just as the logo says, it makes it in spheres that are encapsulating each other. The more you go out from the center of the spheroid, the more you're going towards an older universe. And the more you go in, the more you're going towards the younger universe. And those simulations are used to validate the data that's coming in from the Euclid mission, and in the future by the SKA mission. Do you need to know any of this for this talk? No. But it's always good to have some context. Now, the good thing is, I'm hoping there's no cosmologist or physicist in the audience. So this is my entire cosmology knowledge. So almost like 70 or 80%. So if you do not get any of it, you won't need it anyways in the rest of the talk. And Glass was built with NumPy for CPUs, I think 2 or 3 years back. But the new missions are collecting huge amounts of data, and we have a problem. We need bigger and more fine-grained simulation for these missions. Big number crunching and linear algebra. Everyone knows an answer to that. Just throw some GPUs at it, and it'll start working. That's one thing that Glass needs, GPU support. And the second thing it needs is automatic differentiation for a very specific task, which is compressing data using gradient-based methods. And also, there are always parameters to optimize. So no matter which scientific software I've worked in, they're always trying to optimize parameters. And at the end, they're always looking at gradient-based methods. And you need automatic differentiability for that. So Glass needed QPy and JAX support, or because JAX can support both GPU and automatic differentiation. And both of them are needed for recent and future cosmological surveys or missions. But of course, we do not want to rewrite Glass in JAX or QPy. And also, we want to retain the NumPy backend. So what we don't want to do is just have a Glass that works with JAX arrays or QPy arrays. because of course, most cosmologists don't have access to GPUs because GPUs are busy training LLMs. There's none left for cosmology, apparently. Okay, so now we know what Glass is and what Array API is and why we need to implement Array API for Glass, or why Glass needs JAX and QPy support. And now I'll talk about our work for the rest of this presentation. So we've broadly split the work into 4 sectors: typing the code base, testing different backends, building a unified RNG interface, and migrating everything else. I'll go through these one at a time, and this would be a lot of Python, so this would be very apt for this conference. Okay, yeah, and it might look that like the first 3 are only like 5% each of the work, and the rest is like 85% of the work. But as we heard, we're not good at estimates. The first 3 took us like 40% of the time, and the 4th one is still going on, but it'll be like 60% of our time. So talking about typing, of course, we wanted Glass to be typed. A good practice, good for cosmologists, and this should be for any array backend that we add in the future. And doing something like this, adding union types, is not very scalable. Well, one thing is that, if you add new array library support or provider support, you have to extend this with more unions. But the second thing is, maybe you want like D-type information, which we can pass in NumPy types like that. And JAX type does not support it. But we could use a library called JAX typing that supports it, but in a weird way. So you encapsulate your array inside the D type. But also JAX typing supports adding shape information of your array, which NumPy does not allow you to do. So we can see one thing here, that the typing information is not standardized. Sure, we can add a bunch of if-else statement for edge cases, try using generics, and so on, or make like 50 different types and use them for functions wherever we need. But like the whole point of our API was to have a single block of code that works for every provider library, and this is going in the opposite direction. The bad news is there is or was no standardized typing API, which was a problem for us and is a problem for us. And the example that I showcase, it just shows NumPy and JAX, and it just definitely starts swelling up as we add more provider libraries to it. But we do have a standard user API. Why don't we create a Python protocol out of it? So after experimenting a lot with generics and union types and other things, this is exactly what we did. We came up with 2 protocols, very pretty protocols. A quick crash course in protocols is protocols help you to structurally subtype a class. So if you have a protocol with a bunch of methods and properties, and one of your classes implements all of those methods and properties, it can also implement other things, but minimum of those methods and properties, it is said that the class implements the protocol, and this is okay enough to have the isInstance check pass. So you can have the protocol in a separate repository and your array library in a separate repository. They do not have to inherit the protocol, and it just works out of the box. It's like amazing. And so if we use a protocol in a function like this, where we're just doing a normal exponent, and we can work it pass both NumPy and JAX arrays in it, this works perfectly fine with MyPy. So the typing thing looks like it was solved. It kind of solves the problem, right? Now we just have to mirror the entire API standard in these protocol classes, and we're done. But of course, there's something much bigger than Glass. Not every library would have to do it. Like, we don't want every consumer library to have a set of these protocols doing things. We can, of course, write a whole new typing framework for this. But yeah, this should be a tooling that is provided by the API standard itself, and not everyone tries to reinvent the wheel, which is exactly what's happening now. They are making it. They caught upon our discussion, and they're writing a typing framework for it. But unfortunately, due to time and maintainability constraints, Glass uses unions and generic type to type its code base as of now. Yeah, we'll soon shift to the API solution and possibly be their first users. And one of the reasons is we cannot justify writing a typing framework on a science grant. So at the end, they'll ask for how much speed up does your code have, and not like, oh, you made a typing framework for our API. Okay, so we solved the typing problem. The next thing is testing. Now, I was an RSE with no background in cosmology. I still don't have much background in cosmology. And naturally, it is very dangerous for me to see or touch or refactor such an important library without any automated tests. Now, Glass had tests. What it did not have is, once I migrated to Array API standard, how do I know that, oh, the migration is successful? Or like, okay, it is working with NumPy and it was already working with NumPy. How do I know that? Oh, it's working with the standard and with the other provided libraries. So we wanted to ensure that our tests run with every Array backend that we had, while not having to repeat much code. And of course, we could not straight away test the entire code base, given that we were migrating one function at a time. So we wanted to test individual functions with different provider libraries. And again, there is no consumer-focused testing solution provided by the Array API standard, but they distribute a really nice library called Array API strict, which is a strict and minimal implementation of the Array API, which means it is a provider library itself. It's like NumPy or JAX. The only difference is it strictly adheres to Array API, so it does not add anything above Array API. For instance, JAX would have a subset of its API that adheres to Array API, and then it will build upon that. So for instance, it'll add functions like grad or Jacobian and so on. But Array API strict, on the other hand, does nothing. It just implements the Array API. So if you use the Array API strict arrays within your tests, you'll know if you're using something outside of the standard or not outside of the standard. And that's one thing that we use for testing. However, we also wanted to implement tests for every supported library. And why exactly, you'd ask, given that if Array API strict works, then all the libraries should automatically pick up that and start working. Because provider libraries can differ in the non-standardized part of their code. And a great example for this is JAX and NumPy. Mutability and RNGs, both of which are not standardized and both of which we use a lot. So mutability is JAX arrays are immutable, you cannot mutate them. NumPy arrays are mutable. Array API standard does not comment on it. So it does not say that your array can be mutable or immutable. So it's a choice that's left onto you. And let's say one of your functions is mutating an array. It will pass with NumPy. The test will pass with NumPy. The test will pass with Array API strict because it does not say anything about mutation. But the test will fail with JAX, given that the function is mutating arrays. So of course, we want to run the tests with NumPy, Array API strict, and JAX as well. So we want to run the tests with all the array libraries that we support. So we built our own testing utilities on top of PyTest. This was absolutely necessary, and we can justify it in the grant. It's a simple testing framework. You pass the library that you want to use as an environment variable, and PyTest will run the test with that particular library inside class. And given that that library is installed in your environment, otherwise you can install it. Or you can use our task runner Nox and pass the library and it'll install it for you and also run the tests, in this case, run the tests on Python 3.13. And you can set array backend environment variable to all to run it with every supported array library, which is great because we also expose a PyTest fixture. So if you're writing a test for something which is Array API compatible, all you have to do is add an argument xp in your functions. And to access the array library functionality inside, you use xp dot. So for instance, you'll see here we don't import NumPy, we don't import JAX, we don't import any library. We just use xp dot to do all of our array things inside that testing function. And I'll talk about the RNGs later. But okay, we spent a good chunk of time thinking about and writing this testing framework for Glass, and it is maintainable, easily extendable, and thoroughly documented. And this should, again, ideally be refactored out in a standalone or a more generic testing utility, given that SciPy and scikit-learn both have their own mini testing frameworks specifically dedicated to the Array API tests. And maybe more consumer libraries have them too. But yeah, of course, we never got the time. We cannot justify writing a testing framework on a science grant again. Okay, so now we have the typing information, the testing information, and now on to the third part, the random number generators. This is something that was very essential for Glass because we sample a lot of random points for simulations, both at the beginning of the simulation and even in the middle of the simulation, and we keep on iterating on them to get better at simulations. But JAX, as always, with everything, it has a different approach to RNGs as well. Now, I don't think I'll have time to explain this, but JAX's RNGs are stateless and NumPy RNGs are stateful. In a nutshell, what it means is they both have different user interface and also how they work. So if you create a generator, an RNG generator for NumPy, and you keep hitting it to sample a point, it'll sample a new point every time you hit it. For Glass, however, you have to pass a key inside the random number generator. And if you keep passing the same key inside, it'll sample the exact same point. So you have to do something that's called splitting the key and pass a sub key inside your new RNG call. Now, the problem is, again, Array API does not standardize RNG. It's becoming a lot like things that have to be standardized are not standardized. But this is because they're rather tricky to standardize, right? Because it's not that it's just the user interface that's different. It's basically how they work is different. JAX use more functional programming approach and NumPy does not. The questions are like, which interface should we use? Can one interface even support both the designs? Or like, do users even want standardized, or can it even be standardized? And this was a long-standing issue in the Array API repository, which was closed at the end by saying that, oh, there's a lack of ecosystem agreement and we'll come back to it if we need it in the future. And we definitely need it. So these are screenshots from SciPy, scikit-learn, Glass itself, and other libraries such as efax, which are written for JAX. All of them saying that, what do we do with these RNGs, given that we're trying to migrate to the Array API standard? Given that we heavily use RNGs, we definitely need something like right now. So we wrote a wrapper for JAX RNGs. And again, it's a whole lengthy class, which can be looked at in GitHub. But what it basically does is it cleverly wraps the JAX RNG. So inside it's doing the exact same thing. It is sampling by splitting the key. But outside it looks very much like a NumPy RNG. So you can use it with a NumPy RNG interface. However, it has its own pros and cons, which I'll talk about in a minute. So what the tests can now do is use the uRNG fixture, which dispatches either the NumPy RNG or our own written JAX RNG, and both of them have the exact same interface. So in a way, they're standardized within Glass. And the users who need to pass RNG into a Glass function, like generating matter for simulation, can, instead of using JAX RNG, can use the class.jax random number generator and pass it in, and it'll all work in the same function. Now, of course, this is just a solution that cleverly wraps JAX RNGs. It is not a universal solution. It might not even be the best workaround, but it works for us for the time being. Now, we know for sure that this does not work with JAX's JIT. But if you remember, we just need GPU support and automatic differentiation support. We do not want JIT right now, so we were okay with it not working with JAX's JIT. And it might or might not give us speedups on GPUs. We will know that when we perform some integration tests once we've migrated much of our code base. And the good thing is they picked up on a noise again, and they're working on a standardized API for RNG in a package called Array API Extra. Now, okay, we've tackled 3 things that we had to standardize, and the last thing is the actual migration that we have to go through. Now that we've done, we can migrate the code. So we made a big shopping list with issues that have sub-issues that have sub-issues, with each function documented and telling us which function needs what and what are we missing. Some bits were as easy as switching np dot to xp dot and performing some different things. For instance, here you'd see we're typecasting the last result, and also the np dot dot becomes xp dot sum for some reason. But this was simple. Some required us to think a bit. For instance, the initial list slicing gave us an array of a different shape, and Array API did not do us, so we had to come up with a hack using Array API functionality, use xp.take instead. But some required us to do the standardization, so we created a whole issue for that, and we have another class, xp editions, to standardize things that we use. So for instance, we use the gradient function, both from NumPy and JAX. And given that Array API standard does not standardize a gradient function, we did it ourselves locally, and we have more such functions within this class. And then we have dependencies. So we have 4 major dependencies: HealPy and HealPix, cosmology, all of those are cosmology dependencies. And then we have local dependencies, which is libraries that we ourselves develop, Transform CL, FLT, and other libraries, which we're planning to rewrite locally in an array-play compliant manner. And definitely not the entire libraries, but we're only planning to rewrite some of the functions of those libraries that are relevant to us. There are also local dependencies, which are easy to handle because we can migrate them ourselves, given that we maintain them. But there's also one local dependency in C, which now dispatches either JAX functions or the C-binded functions as per the request. So it is now not as generic as it should be because it will only work with JAX and NumPy, and it'll error out with any other thing, but it can be easily extended to, say, QPy or Dask whenever we start working on those backends. Oh, okay, that was a lot of work for something that looked simple. That was just that standardized the API, and yeah, it should be just switching NP dot to XP dot. But we are getting somewhere at the end. We have done a lot of work. A lot of work is in progress. So that migration issue, you'd see a lot of issues are still open. We're still working on them. We've made a lot of suggestions upstreams, and we've made a lot of contributions upstream too. And it has been quite a lot of fun working on this cutting-edge scientific Python thing. So like working on a standardization spec when the spec is itself being developed, that's quite challenging in my opinion. And yeah, that was all of our work. So some quick key takeaways before I finish my talk. It's mostly about our API. Would be that, it is an awesome thing. It was a big achievement to standardize the APIs of such big Python libraries like NumPy and JAX and QPy. And even TensorFlow and PyTorch are opting for it. But the standard is relatively new. It is under active development, including the tools that you would have seen from my talk. So there will always be features that have not been implemented. There will always be open issues in the standard. Now, big provider libraries like NumPy, JAX have already moved to the standard. Some others are moving, but not everyone has made the transition completely. So you will go through hiccups such as QPy and Dask. They're still in the process of migrating. And as far as I know, scikit-learn has also not completely migrated as a consumer library. SciPy has, and Glass is still in the process. The team is super helpful and welcoming, but big open source projects and enough human power, like that never happens, right? So all of this, all of the cons that I'm talking about, it's still under development. It can be carried out relatively easily, I believe, but they just don't have enough human power to carry it out. So good news is the team is helpful, they're welcoming. So if you are interested, you can go ahead and make some contributions to the standard. Yeah, that was all about our API, Glass, and what we're doing with it. Thank you.
Thank you. So, we have time for a few questions. Are there questions in the audience? Otherwise, I would have a question. Is there like a measurable performance overhead of like just the pure NumPy to now having the abstraction? Were you even interested in this, if there's an overhead?
We were not interested in this, but there ideally should not be an overhead, given that it's just replacing NumPy with XP, which is just an alias to NumPy at this point. So technically, there should not be any overhead.
Nice. So it's a zero overhead abstraction, or almost zero because it's just almost zero, yes. Not measurable because the heavy lifting still runs on NumPy. Yeah. Mm-hmm. All right. Are there other questions in the audience? Over there?
Yes. So my question is, if everything would be standardized, the whole IP, what was the reason to have different libraries if they kind of all do the same or have the same interface? Because before it was something, every library had its strengths and weaknesses, or I like this API more than the other.
So the idea is to standardize only the core of the API, which is the basic array operations. That's why things like gradient functions are not standardized, things like mutability is not standardized, and things like random number generators are not standardized, which are very opinionated. So I think they're only standardizing the core subset of the functionality.
Okay, thanks. That makes sense.
All right. think there don't see any raised hands, so let's continue with the lightning talks. Thank you very much.
Yeah.